Hey guys, let's take just a second to review the combined gas law that we talked about in class yesterday. Remember, we have the pressure-volume relationship Boyle's law, the volume-temperature relationship Charles' law, and the pressure-temperature relationship Gay-Lussac's law. There's a little bit of additional information we want to be able to work with the combined gas law, and it's this idea of Avogadro's principle, that equal volumes of gases, if they're at the same temperature and pressure, have the same number of molecules. We're going to use that for another law, the ideal gas law, a little bit later. So if we go back to Avogadro's principle, we see this idea of equal volumes of gases at the same temperature and pressure. We're going to call those kind of generic temperature and pressure conditions STP, or standard temperature and pressure. This is listed on your Chem Helper as 0 degrees Celsius and 1 atmosphere. When we have these conditions of standard temperature and pressure, 1 mole of any gas, it doesn't matter if that is oxygen gas, carbon dioxide gas, nitrogen gas, carbon monoxide, any gas at the conditions of standard temperature and pressure is always going to occupy a volume of 22.4 liters. So here are the couple of sample problems that are in your worksheet packet on page 8. Let's take a look at how we work these out. So the first question is asking how many molecules of hydrogen gas are in 3.72 liters. Notice that it's at STP. Knowing that, I know that 1 mole of gas always occupies a volume of 22.4 liters. So I can start with liters, cancel liters, go to moles, and then convert from moles to molecules, and I should end up with 10 times 10 to the 22nd molecules. In the next example, we want to calculate the volume of 0.881 moles of gas. Again, if it's at STP, I know that 1 mole of any gas has a volume of 22.4 liters, and I can easily convert from moles to liters to get 19.7. In example letter C, we're using 5.6 cubic decimeters of a gas. That cubic decimeter is exactly the same as a liter. So I can use my molar volume to convert from deciliters, which cubed, which is the same as a liter, to moles of oxygen gas. And then in problem letter D, knowing that I have 0.25 moles of gas and that the molar mass of oxygen is 32 grams per 1 mole, that sample of gas would have a mass of 8 grams.